Well, good afternoon, everyone. Thank you for being here this afternoon. I want to welcome everyone to our third research conversation of this fall semester. I also would like to use this opportunity to thank all of you for attending many of these research conversations. It really helps us promote and continue to advance the culture of research in our college. Today, Dr. Peng He will present on integrating generative AI into three-dimensional learning progression, supporting teacher instruction and student learning in science education. He will present insights from his recent NSF-funded project that focuses on how generative artificial intelligence is being integrated into standards-aligned learning progressions to enhance both teacher instruction and student learning in science education. He will also discuss the future opportunities and challenges of employing AI in K-12 classrooms, drawing extensively from his research and collaborative partnerships with schools. Dr. Peng He is a scholarly assistant professor of science education here in our college. He holds a master's degree and a PhD in curriculum and instruction from Northeastern Normal University in China and the University at Buffalo, respectively, with extensive journal over 40 published journal articles and book chapters. Dr. Peng He has shared his work at prestigious national and international conferences such as AEHRE, NAST, and ISLS. He also serves on the editorial boards of leading journals, including the Journal of Research in Science Teaching and the International Journal of Science Education. Currently, Dr. He is co-editing a special issue titled Opportunities and Challenges of Using AI in Science Education, and that will be published in Disciplinary and Interdisciplinary Science Education Research. Thank you so very much for being here today, Dr. Peng He, and please join me in welcoming Dr. He to our research conversation today. Thanks. Over to you, Peng.
Thank you so much, Shola, for your very detailed introduction about myself. And also thank for AJ and Laura to organize this section, and also all of you come today to this research talk. Let me share my screen first. Okay. Can you see my screen now? Okay, cool.
Yes.
So this is a great opportunity, I can share my work and have a conversation with our colleague at WSU and also student about my research work. So to start my research in deep, first I want to introduce a little bit about my background, and then I will talk about my project, how I integrate AI with learning progression in science education research. And it includes two parts. One part, support student learning over time, and another part, how to support teachers in real-time instructional decisions in the classroom. And the last, I will share my thought about the future, how we can use AI in science education. So about myself, so this is my career trajectory before I joined WSU. I obtained my doctoral degree in Northeast Normal University, which is one of the top teacher university in China, and also it's a joint program with University of Buffalo. I studied 2 years at University of Buffalo. At that time, I have equipped me have a strong knowledge about how to conduct quantitative studies in science education. So after I came back from University at Buffalo, I joined my home university as assistant professor for 6 years actually. I actually on site it was 3 years, and in 2019 I came back to US and joined Michigan State University as a postdoc research and also research assistant professor over there. So at that time, so when I was in Michigan State, I heavily engaged in the standard-based learning environment design, include curriculum materials assessment, and also led on after pandemic. So we are starting to look at how we can integrate artificial intelligence and also learning analytics into this learning system can better support teacher instruction and also student learning. So I summarize my research line into three lines. The first one is about how to employ design-based research and also advanced quantitative method to develop, implement, and test science learning environment, especially in the K-12. Actually, it's secondary level, middle school and high school learning environment. The second one is apply, advanced quantitative method like cognitive diagnostic model, factor analysis, Russian modeling to design instrument, both teachers and students. And the latest work is how to leverage machine learning, generative AI, to enhance teacher practice, student learning in science education. Yeah, this is in the US. Before I joined WSU, what I have been involved in several projects. So I started with NGSS aligned assessment, which is not multiple choice. It's a performance-based assessment. And starting from that point, I joined another project we call CESE, which is high school assessment curriculum design. We use project-based learning approach. And so the PASTA project is about how we can use machine learning to automatically scoring student responses on the performance-based assessment. And in the center part is my own project as a PI. So which is how we can design and test their learning progression for middle school students um, to learning science, physical science core ideas, incorporate science and engineering practice and cross-cutting concept together, which is aligned with the standards, so that they can promote their learning over time. So so for today's talk, I will mainly focus on my own project, which is three-dimensional learning progression. Oh, my current research focus, like I say, I have a three line, right? But currently, I'm put my effort how to leverage artificial intelligence to design and test a long-term learning system to support student deep learning across K-12 and beyond. And this is, how I vision myself. So all in all, I work closely with teachers, with students in the classroom. So this all my design things is come from my collaboration with teacher and student, and try to support teacher and student in the classroom. And this is the whole system, and the whole system want to promote student learning. So which we call is knowledge in use. So for knowledge in use, it's aligned with the new visions in the latest NGS science standards we call next generation science standards. And the key part is integrates knowledge in use is integrates. It's not about memorize content. It's about how student can apply what they learn into practice to figure out the problem, to solve the real world problem related to the science. So it's kind of like, it's more complex construct than, previously we only focused on, core ideas, content. Yeah. So this provide a very challenge how we can promote student learning, and also a lot of teachers, especially for the novice teacher. So they need, the heavily training professional learning, understand the standards, understand the three-dimensional learning, understand, how to teach in GSS aligned curriculum materials, and also assessment. Assessment is not, assessment of learning, it's an assessment for learning, right? How we can use assessment formatively in the classroom. So it's all new when the NGSI standards come out. And in my work, my latest work is how to integrate AI into learning progression. So this is one example in my project we are developing about learning progression. So you can see I use the for the diagram I use the color, right? I use the color which have the blue, orange, and also green. It's a three-dimension component, and that means our learning progression is not, learning progression. So research have two critiques. One critique is about, learning progression is a model, is a simplified model, right? That, have the unified pathways that all students need to follow the same pathway to move from low level to the up level. This is the first criticize about learning progression. Learning progression is always about, summative assessment, and also based upon summative student performance on summative assessment to diagnose exam student levels, but it's not helpful to support student learning. That's, we based upon the standards to think about how we can leverage learning progression to support student learning and the teachers teaching. And more importantly, learning progression in our philosophy is not about the unified learning pathways. We provide multiple learning pathways that you can see the different arrow, the left side and the right side. That means, when teacher teach this topic, so this topic is about chemical reactions. It's not about, all teachers will follow the same the same way to teach student, right? It's based upon student prior knowledge. Teacher can use our learning progression as a framework to guide their, adaptation about curriculum materials so that, they can accommodate their student needs based upon student background. That's what we mean by learning progression with multiple learning pathways. This is, we push the learning progression studies forward about at this part. And, learning progression, as I said, it is a guideline. It's a framework that can guide the learning environment coherently and also in the long-term perspective. In our study, we always, like for the middle school level, right? For the physical science, you always have a multiple unit. Our learning progression can provide a guideline to help teachers to think about, okay, which unit come first and which unit comes next that student can build upon what they learn from the unit one that can help them to learn the second unit, the third unit. This we call it is intercoherent unit, inter-unit coherence. And also inside one unit, we have several lessons because we use project-based learning approach. Usually, project-based learning unit have like 10 lessons. So our learning progression help teachers to think about how we can arrange lesson sequence based upon, student the ideas learning progression one by one. So let's learning progression can guide the coherent about the learning environment. We already have the empirical evidence from one of the study, the field test study across Michigan and California, that our learning progression can guide the student learning across time. So, but still, teacher meet challenge when they, apply learning progression into their curriculum material. They need support. They need support, especially in the classroom support, right? That we are thinking how we can integrate artificial intelligence that can be implemented in the classroom that support teacher to make the decision. Because when we use performance-based assessment in the classroom, so usually, performance student responses on the performance assessment, they have two formats. One format is the written response, like a short paragraph, explain their understanding. Another format is we call it the modeling task, which is drawing a picture to describe why the phenomena happened. So in the drawing models, it always shows student understand about the mechanism about the phenomena occurs. So, but in the classroom, it is very challenging for teacher to provide feedback. Teacher always, review all of students' responses very quick, and then organize a group discussion, right? And then some teachers, they just put it aside. Then after class, teacher will take like 1 week or 2 weeks to get all of analysis done and provide the feedback, right? We thought how we can, use AI to provide timely feedback, meaningful feedback for students and teachers, so that teacher can move up from the low level to the up levels, to promote student learning over time. So for the artificial intelligence, we think about three lines. One is provide timely information about student responses in the classroom. Another part is provide personalized feedback and also immediate teacher feedback on that. So here's the real class scenarios, because like I said, so assessment is not just, it's for learning, it's support student learning. So teacher usually use our assessment in the classroom. For example, for this assessment task, so we provide, step 1 to step 5. It is lab experiment, and then we provide the data as evidence, and we have students to come out, their own claim, and also find the evidence from the data table, from the diagrams, from the step 1 to step 5. And then, in the question 3, it's all about how your evidence can support your claim. So what is the key core ideas you want to include to explain why your evidence can support your claim? So this is one of the assessment tasks in the classroom. Students need to write a short paragraph to explain that. And then, so in one example, like I said, 20 students complete the task. Teacher review, right? And teacher need to prepare feedback. It's time consuming, and teacher cannot prepare well in the classroom. And we use for our design framework, so we use human-centered design approach that we consider, we always bring human in the loop. And for here is a content expert and also teacher in the loop. And we have, like several phase from the assessing phase. We have scoring phase that we use. So previously we used machine learning. I will show the result. And then we have an interpreting phase that provide individual student performance and also collective student performance based upon our three-dimensional learning. So in the feedback phase, we provide student feedback and also teacher feedback. And the last, so because even the feedback is not enough, teacher, especially for the novice teacher that don't have a three-dimensional experience, then we provide some instructional strategies that, can, when they read the automatic report, they have the instructional strategy support their make the decision. So this is the example I just show to all of us. And this is the one of the student responses. You can say, okay, claim. So yes, because when we mix two liquids together, it makes a new substance. And then have the evidence, density, boiling point, reasoning why this is important, right? So for our rubric, coding rubric, scoring rubric, we have this analytical rubric to see the absence or presence about the criteria. For example, for this student responses, clearly it missing the C4, C5, and C7 component, which means, student may already achieve the practical concept, but they have challenge. See, they have the challenge to understand the core ideas that we think about how we can provide student feedback. Oh, so after we have the analytic rubric, so we think about how we can use machine learning to score student responses. At the previous project, we call the PASA project. So we have the human to score at least 1,000 responses to training the machine, computer. But it's time consuming for the human scoring because at that time we still don't have the large language model in hand. We spend a lot of time to match, to train the machine to like the human to generate the scores. That's the previous approach. And then after that, we have the score pattern. Like this one is 1110010. That means this student, they achieved the practice, which is a construct explanation, and also the data pattern, but they need support in the DCI component. Then we think about how we can programming student, provide individual student feedback. It still use our analytic criteria. So always we say, okay, your responses clearly state achieved this part, like chemical correction occurs with the evidence. But so instead of we give their what they're missing, but we prompt them to think about, okay, your response may also consider why data pattern can be used as evidence to support your claim because it is missing in student responses. So that's the individual feedback. So it's not like large language model to contextualize student responses because we still use machine learning approach. That we have the programming student score pattern that we can generate individual student responses feedback. Another component, like I said, introduced before, because teacher reads the report, right? Teacher makes sense. Okay, how many my student already achieved all three dimensions in my classroom, and how many students they achieved the core ideas, but they need support in the practice, and maybe some students left behind all the 3Ds, right? Teacher needs to think about what should I do next. And at that point in our studies, we provide several insight strategies. We based upon this is our framework. We consider teachers' pedagogical content knowledge for the content-specific strategies. We consider general strategy. We use Mickey Chase ICAP as a framework to constructive and interactive engage students from our insight strategies. And then we consider about inclusive strategies. We consider the language accessibility and connections. So that this is the framework to help us to design insight strategies that align with the task, align with the standards that can support teacher to make immediate decision in the classroom. And within all of that design materials, we design the teacher dashboard design. So from the color blue. So instead of we have the 3D missing the core DCR that part, we use color. So color means like the blue student need all 3D support, and the pink means student already achieve all of the 3D understanding. So teacher will immediately have this kind of group feedback, and also teacher also have the individual student feedback. If teacher click student name, they can see individual student informations. And in the right side, it's about our insight strategies. How summarize about student. What do we mean by group blue? It is for the teachers. So what is insight strategy you can use based upon student, their your student performance in the classroom. So basically, this is the teacher what the teacher dashboard design. So we already done this part. And this is next step because in our PASTA project and also in my 3D learning progression project, we haven't yet talked about how AI can empower teacher decision making. So still, teacher still need to manually to choose in such strategies, even already have the auto score, right? In the next step, we're thinking about, this is the framework I came out, how to leverage learning analytics to have student demographic information, their prior learning experience, and also teacher information like teacher teaching experience, which in GSS, all of these, we can fit in the classroom that we can use data mining as an approach that can see, okay, given student performance in the classroom, given the materials student use, and also given student and teacher background, and AI can automatically recommend our expert in such strategy from here that can hybrid information filtering from all of the information we feed in the system, that AI will recommend one of the strategies, just fit in teacher and student needs. And teacher have the authority to decide whether I want to adapt or refuse this AI recommend in such strategy. That's not like, teacher just deliver, right? Always AI is the partner. It's not like replace teachers workload. In the teacher always in the loop to make the decision instead of AI. Then teacher can support student learning, take actions. So this is having yet to get there, but we already have this kind of framework that guide how we can promote our studies in the future. And I will skip this one. So because, like I said, previously we only use machine learning approach, but we found several challenge. One of the challenge, machine learning always want to learn from massive human coding data. So we spent like 2 years on the thousands human coding data, right? And it is not efficient. And also machine learning algorithm doesn't work in the classroom. We found it a very challenging and stressful. When I observe teacher use our platform in the classroom, so even their rating responses, even their very mirror, just change several words, but AI give different scores, different feedback. That puts students stressful and also teachers stressful, right? So we think about, okay, that's probably not a better way to do that. Why not we just, not grading, not score student responses, but just provide student and teacher meaningful information about student understanding. And at that moment, we have large language model and generate AI. So we think about how we can integrate artificial intelligence into learning progression that can support, that can provide teacher meaningful information about student understanding. And this is from my learn progression project. This is, we have the paper pencil one. We have student always, drawing picture. This is a picture drawn to show their understanding. And this is the handwriting. You can see, but, large language model doing a great job to recognize student handwriting. So that's very impressive when we do, study, pilot study on this part. And so for the large language model, it's not like I said, it's not like human coding thousands of data. So you just want to give, the criteria and your rubric and also give examples. So let large language model to learn from these examples so that they can, not grade student responses, but provide meaningful information. And also, large language model also can provide a rationale why I give this, identify these levels. This is my explanation. And human, our content expert, always in the loop to see whether it makes sense or not. And instead of 1,000 human coding, we only have several examples that we can feed in large language model and have them to learn from the human coding, and then have the reasoning process to analyze student responses. So this is a procedure how we do that. So usually, we use the retrieval augmentative generation, which is, we call the RAG approach, that we fit in our NGSS standards, we fit in our design approach and also examples, so that the large language we can, large language model is it's very general. It's not domain specific. That's why we want to fit in all of these design materials to the large language model, so that the large language model will have the capabilities to understand our context, which is situated in the next generation science standards, right? And we have the initial criteria, samples, and always we have the human in the loop, so that we can check whether, if human makes mistake or the large language model makes mistake. And typically, it's like I said, sometimes as a human, it's still challenging for the human to recognize the student handwriting from the paper pencil, right? And this large language model sometimes can capture what we are missing when we, doing this kind of work. I think, human and the large language model can learn from each other in this perspective. And this approach we call is field short prompting. That we have, several examples. We have the prompt questions to the GPT model. Then, and we will have the testing data to see whether, large language model analyze its match with human code or not. So it's an iterative process to train large language model to have the capability to analyze student responses. And yeah, so for training the larger model, you can see when we provide examples, we also have different strategies. For example, so one of our strategy when we want to enhance large language models capability is human also provide the scoring rationale. Why human to see, and also color coding student responses, like say, okay, orange color. So it represents student understanding about the core ideas, Large language model can learn from that and generate the similar reasoning process like the human. So, that's a process we take carefully and iteratively so that, to have large language model to understand. And this is the GPT workload. Given the time, we probably don't have the time to go through the details. And yeah, this is the result for our 3 assessment tasks we are trying to analyze. And it is, you see, it is not very helpful. So the human, the large language model, you can see the percentage. It is not very high, especially for the DCI, which is core ideas. For the practice and concept, you can see, yeah, sometimes texture already 90%, 100, right? 85% at least. But for the DCI part, still a little bit low. So that's another challenge because large language models still not well trained, even we fit in a lot of materials like standards, right? But large language models still not content specific to identify student responses to address the core idea sections. So let's push us thinking forward how we can train large language model to more specific to our context. That's, Tim and I will collaborate with computer science and we submit several grants this year. So we want to resolve these problems from this kind of studies. Yeah, this is the one of the, we have the vision settings. That means the GPT model just recognize the handwriting immediately, right? To give give analysis. Another is we also have the human to translate student handwriting to into tests into our Excels so that we can compare. Apparently, when we have the human to translate student handwriting to the computer words sentence, is the accuracy is much better. It's right. But we think about how we can empower large language model, especially the latest version, the GPT-4o, right? Have the even more power to recognize the images immediately instead of the human in the loop to translate students' handwriting. So that's another challenge we want to address in our future studies. So given all this, in mind, this what we have already we have been doing so far, right? We think about the future directions. So one is about leverage the data analytic approach, like learning analytics, right? To think about how to build the AI recommenders for teachers that the teacher can support teacher to make the decisions. And the second part is about, learning pathway. Like I said, classroom is not a unified one pathway, and teachers across the nation, they use different curriculum materials, even they all address the standards, right? So our learning progression provide a framework guideline to think about, okay, how you want to arrange your lessons and also align the assessment in your lesson plan. And one thing is about computerized adaptive learning that you can leverage our three-dimensional learning progression assessment into the classroom, right? We can based upon student performance on the assessment can use the adaptive learning approach that can recommend the next task, like the TOEFL, right? So for the TOEFL, so teacher always answer one question, and the machine, so given the programming, can recommend the second one, given student performance on the previous lessons. And also another approach is to use the cognitive diagnostic models, right? To diagnose student response. It's not exam or evaluate student understanding. It's about diagnose student weakness so that we can provide timely and also a specific feedback for student to promote their learning. So that's about the second part we are thinking about. And also a very key component in science education is about, how to incorporate the diverse student background in the context, like in our Eastern Washington, right? So our school district, rural areas, right? They have their unique experience, and also so local communities. We think about how we can adapt. We can have teacher adapt assessment, incorporate their own background, so that it's not like we provide assessment. So we provide assessment as example and have teacher to adapt assessment into their context. That's one of the idea we submit this year NSF grant to support teacher adaptation about assessment in the classroom. And the last one is because I'm interested in the learning system, the learning environment. Learning environment is not about assessment. Also have curriculum materials, professional learning, right? I'm thinking about how AI can be a partner in different component in the learning system. So one of the project we're doing, so it's about how to facilitate classroom discussions in the classroom, use argumentation to learn as a framework. So AI can be a partner to facilitate classroom discussion, argumentation activities in the classroom so that they can achieve the levels in the classroom so that they can move forward to the next levels. So yeah, this in the future, and right now we are doing for our counter research. I think given the time, so we have 10 minutes. I will stop here and taking questions from all of us. Thank you so much.
Thank you so much. That was wonderful, very fascinating. So David Slavitt asked the first question in chat, so I will let him start the discussion.
Okay, cool.
Hi, Peng. Thanks, Laura. Yeah, thanks, Peng. I have a couple comments and then a question. I really like the formative assessment aspects of your model and your work, both in terms of the students, but then also the teachers, where you had these instructional strategies that could be generated for ideas. So there was sort of formative assessment at two levels. You mentioned that the content person is always in the loop, and it made me think of, a fourth grade teacher who may not have terrific science content knowledge, which isn't a far-fetched idea. And what would happen in those situations, and let's say their student used GPT to produce work, and it gets sent to the teacher who relies on the GPT to assess it. You got machine grading a machine. So I go to those places, I guess, when I think about this. But my question is about I guess my search is how to make this as close to human thinking as possible. And I know that's where your heart is as well. And so it got me to sort of what I could be wrong, what I gather is sort of the core of all of this, which is the learning progressions that you talked about. And that's kind of a base for all of this. And I'm just wondering where they came from. Are these hypothetical, more theoretical in nature, or are these grounded in data of actual student thinking and work?
That's great questions. Yeah, like I said, it's from my three-dimensional progression project. It is a 3-year project. For this year, I transfer my grant from MSU to WSU. This is the last year. So in our year 1 and year 2, we collect. So we based upon standards, unpacking standards. We have the hypothetical learn progression at first. Then we conduct student interview. So we collect like 60 student interview across several districts, and also span from grade 6 to grade 8, so that we can cover all of the ideas we want to cover. So based upon student data, analyze student data. So we have the empirical evidence to support student levels on the learning progressions, and also we have assessment. So this assessment is not new created assessment from my project, because like I said, I was working on one of the assessment projects for several years. So I use that assessment already being validated from that project. I borrow that and contextualize into my learning progression and filling in the levels. And also we use think aloud student data so that we can place assessment tasks into our learning progression. I can say in short, our learning progression, both we have the hypothetical perspective based upon theory, and also we have the data directly from student interview data to support that. And also, our learning progression is not a one-time learning progression. So that's why, so in my second year and third year, so we have teacher to implement learning progression. So we're collecting data from teachers' implementation, and also students use our learning progression assessment across time, right? We use that as evidence to iteratively revise our learning progression in the second year and third year. So that's the approach. We use the design-based research to conduct a three-dimensional learning progression research. Thank you. Thank you, David.
Thanks so much. Do we have any more questions? It's about 12:55 right now. Maybe just speak out, anyone, if you've got a discussion point. Thank you, David. That was excellent. Do I see your hand, Marcus? Okay.
I would just say thank you. Thank you so very much again, Peng. Excellent work, really good work. I see this work connecting with many other faculties' work in our college, science education, educational psychology, psychometric analysis. There's a lot of work on learning theories there, ICAP framework, so many areas of connection for the college. So this is really exciting. And hopefully we will be having large grant applications from faculty in the college teaming up with you going forward. Thank you again. This is really such a good piece of work for the college. We really appreciate your work. As you continue to do this work, I would just give a charge that we continue to look at how do we get this type of tools into the classroom.
Yeah,
I think that would be, we do excellent work in academia. It's great work, but the questions that many people often ask me when I go have maybe fundraising or talking with people is the practical side of things. How can this be used in our K-12 classroom? So as you continue to do this work, I hope that will be part of your research agenda too, thinking about how do we work this into our K-12 system. Thank you again, Peng. Any last minute questions about 1257, 58 here? We would have a series of research conversations in the spring where we are lining those up as we speak. And hopefully we should be able to announce the first one before the end of the year. Thank you again for being here today. Interesting presentation, Peng, and we look forward to many collaborations coming out of this presentation. Have a great rest of your week, everyone.
Thank you so much, everyone.
Yeah.